Can you believe that in just a few days in complete darkness, bean sprouts, those tender, crisp, white shoots born from mung beans, can become the soul of millions of dishes while powering a multi-billion-dollar industry few would ever expect? What has transformed these tiny beans into a massive industrial flow, producing millions of tons of sprouts each year? The remarkable journey of this special microgreen begins with carefully selected mung beans, germinated in darkness. Within just a few days, they grow into plump, crisp, white shoots. From there, they are harvested in sealed stainless steel tanks, processed through modern production lines, and swiftly delivered to supermarkets and restaurants, ultimately becoming the familiar vegetable on family tables around the world. Today, join Agriculture Insight as we step into the world of these fragile yet vibrant white sprouts and uncover the secrets behind their enduring appeal. All will be revealed in this video. Bean sprouts, mainly mung bean or soybean sprouts, are a type of sprout vegetable with a long history in East Asia, especially in ancient China, before spreading through trade routes to many other cultures. Since ancient times, they have been both a humble food source and regarded in traditional medicine as a healing vegetable that helps clear heat and detoxify the body. Unlike other vegetables that require sunlight to thrive, bean sprouts are grown entirely in the dark to keep their stems white, plump, and crisp. Within just 3 to 7 days, a tiny dry bean can increase in size several times and become edible. Remarkably, during germination, bean sprouts self-generate vitamin C, a nutrient almost absent in dry beans, making them an unexpectedly rich source of nutrition. However, the warm and humid environment that favors sprout growth is also ideal for bacteria, so although they are often called soil-free vegetables, bean sprouts are generally recommended to be eaten cooked for greater safety. Today, East Asian countries such as Japan, Korea, and China remain leading centers of bean sprout production and consumption. Despite their extremely short life cycle and low market price, the global sprout industry still generates billions of dollars in revenue each year. More importantly, bean sprouts are considered a sole vegetable in many Asian cuisines, appearing everywhere from simple family meals to street food and even fine dining restaurants. In just 100 grams, bean sprouts contain only about 30 kcal, but provide up to 3 grams of protein, along with abundant vitamin C, folate, vitamin K, and fiber. This surprising blend of nutritional value and widespread popularity makes bean sprouts a tiny wonder of the culinary world, simple yet unique and almost irreplaceable among vegetables. Now let's begin our journey of discovery, starting inside large-scale sprout production facilities, where each tiny mung bean is awakened to begin a new life cycle through modern cultivation methods. The very first step, which may seem simple but is absolutely crucial, is seed selection. To produce a batch of white, plump, crisp, sweet, and uniform sprouts, mung beans must be carefully chosen. Only round, firm, evenly sized beans, free from mold, pests, and with a germination rate above 95% are accepted for production. Before use, each batch of seeds undergoes strict quality inspection and is then stored in specialized cold rooms where temperature and humidity are consistently controlled to preserve freshness and germination capacity. When production begins, the seed bags are taken out of storage and poured into a loading hopper, which feeds them directly into warm water tanks maintained at about 35 to 38 degrees Celsius. This soaking stage lasts for several hours, allowing the beans to fully absorb water and swell evenly, while discarding any hollow or damaged beans that float to the surface. The purpose of this process is to awaken growth, activate the embryo inside each seed, and prepare them for the next germination stage. After about 8 to 12 hours of soaking in warm water, the beans are transferred into cool water to be refreshed, then placed into vertical stainless steel cylinders or specialized sprouting trays. From there, they are moved into sealed germination chambers, where the temperature is kept stable at 24 to 28 degrees and the air humidity maintained at 90 to 95%. Throughout the 4 to 6 day germination period, an automated system sprays clean or sterilized water several times a day, keeping the beans moist without flooding them. Light is completely excluded, allowing the sprouts to develop white, crisp, and plump stems. When the sprouts reach a length of about 4 to 6 centimeters, the germination containers, now filled with thick clusters of white sprouts, are transferred to the preliminary processing area. The masses of plump white sprouts are emptied into a collection hopper and sent directly into the automatic pre-processing system. This crucial first step separates the sprouts from the germination environment and prepares them for the cleaning line. As soon as they enter the processing line, the bean sprouts pass through a rotating shaft fitted with steel prongs and scraping teeth. This mechanical motion helps remove the long roots and any remaining seed coats from the sprout stems. As a result, the product gradually becomes cleaner, more uniform, and suitable for commercial presentation. The byproducts, such as roots and seed coats, are collected in large plastic bins for disposal or reuse as animal feed. After the root removal stage, the sprouts continue along a mesh conveyor belt and pass through multiple layers of strong water jets from a high-pressure spraying system. The continuous flow of cold water not only washes away impurities, but also cools the sprouts, helping preserve their crisp texture and natural white color. In certain steps, the sprouts are also soaked in clean water, while vibrating sieves separate out undersized, broken, or substandard sprouts. To ensure food safety, modern production lines are additionally equipped with misting or ozone water spraying systems. This step helps minimize the risk of bacterial contamination and extends shelf life. Rapid cooling directly on the conveyor further enhances freshness retention before packaging. After washing and disinfection, the bean sprouts pass over an inclined mesh conveyor to remove excess water. Streams of compressed air or cool airflow are blown strongly from above, allowing the sprouts to dry quickly without being damaged. At this stage, the sprouts have reached the desired level of cleanliness, whiteness, and crispness, and continue moving along the conveyor to the weighing and packaging area. Here, the bean sprouts are dispensed into a multi-head weigher, an advanced device capable of portioning products with gram-level accuracy. Small hoppers rotate in sequence, opening one after another to release just the right amount of sprouts into collection chutes. Thanks to this process, every finished pack consistently meets the factory's weight standards, typically 200 grams, 500 grams, or 1 kilogram, depending on market demand. Immediately after weighing, the sprouts drop straight into the automatic packaging machine. Pre-rolled food-grade plastic film is cut into segments and opened beneath the filling spout. As the sprouts fall in, the bag opening is clamped shut and sealed by heat. At the same time, the machine can either remove excess air or inject clean gas, nitrogen, to extend shelf life and keep the sprouts fresh and crisp. Finally, all finished products are vacuum-packed, placed into cartons, and stored, ready to be distributed to consumers. But what if you tried growing your own bean sprouts at home? In fact, cultivating bean sprouts is incredibly simple and fun. This sprout vegetable hardly requires any soil, just clean water, darkness, and a little patience, and you'll have a harvest. They can thrive in almost any container, from small pots, bamboo baskets, tin cans, or even cut plastic bottles, as long as there is drainage and no direct exposure to light. The process begins with carefully selected mung beans, round, firm, and free from pests. After soaking the beans in warm water for 6 to 8 hours to allow them to swell, rinse them thoroughly and place them into your chosen container. Then cover with a damp cloth to maintain moisture and block light. Each day, rinse the beans 2 to 3 times to keep them moist but not waterlogged. After about 3 to 4 days, plump white shoots will begin to sprout, and within just 5 to 7 days you can harvest. At that point, simply pull out the sprouts, wash off the roots and seed coats, and they're ready to be enjoyed in your dishes. Bean sprouts have long been an indispensable part of Asian culinary culture. In Vietnam, they are a familiar companion in nearly every dish, from iconic specialties like pho, bun bo, and bánh xèo to everyday family meals, always bringing a perfect balance between richness and refreshing crispness. In Thailand, bean sprouts are the soul of the famous pad thai, where each fresh sprout blends with noodles, shrimp, and tamarind sauce to create an unforgettable freshness. In Japan, moyashi are quickly stir-fried or added to ramen, serving as an affordable vegetable embraced by all social classes. Meanwhile, Korea has built an entire food culture around bean sprouts. Sukjunamul from mung bean sprouts and kongnamul from soybean sprouts, most famously in the hangover soup kongnamul guk, often regarded as a true national dish. Beyond being a versatile ingredient, bean sprouts are also popular for their low cost, ease of preparation, and adaptability to many cooking methods. Eaten raw in fresh vegetable assortments, mixed into salads, quickly stir-fried with meat or seafood, or added to hot pots and soups. In any form, they retain their signature crisp freshness, softening strong flavors while adding extra nutrients, making bean sprouts a humble yet irreplaceable sprout vegetable in East Asian cuisine. Just one cassava root can take a life, if not properly processed. It may sound exaggerated, but the truth is that cassava contains cyanogenic glycosides, which when broken down release hydrogen cyanide, HCN, a deadly toxin that can cause death in just a matter of minutes. Despite its inherent risks, cassava is a paradoxical crop that humans have domesticated and spread across the globe since the 16th century, primarily through colonial empires, where it quickly became a staple crop and laid the foundation for a multi-billion-dollar starch industry. And from there, throughout history, cassava has time and again played the role of a silent hero, saving millions from famine across Africa, China, India, and even during the Vietnam War. That's why, in Africa, cassava is seen as a symbol of life and the unyielding will to overcome hardship. Compared to potato and sweet potato starch, cassava starch contains a higher starch content of up to 80 to 85% and stands out for its strong thickening power, high clarity, neutral taste, and low cost, making it ideal for both the food and industrial sectors. Like every legend, the journey of cassava begins with Mother Earth, where humble cuttings grow through sun, wind, and time, beginning a new life cycle for a crop that nourishes millions. In early spring, as the land welcomes its first rains after the dry season, weather conditions become ideal to begin a new cassava growing cycle. Unlike many staple crops that are grown from seeds or seedlings, cassava has a unique trait. It is propagated using stem cuttings from the previous harvest. Healthy cassava plants are carefully selected after harvest to serve as mother plants, a crucial step as the quality of the stem cuttings directly affects the sprouting rate, growth performance, and yield of the next generation. The selected stems are then trimmed into cuttings measuring 20 to 25 centimeters, each with 5 to 7 healthy buds to maximize sprouting potential. Before planting, these cuttings are often treated with antifungal solutions to to prevent root rot and pest damage. Another important factor is soil preparation. The land is deeply tilled to a depth of 30 to 40 centimeters using mechanized plows, creating optimal conditions for root development and making future harvesting easier. A common planting distance of 80 by 100 centimeters provides enough underground space for tuber clusters to grow, while also ensuring compatibility with modern harvesting machinery. Today, in many specialized farming regions, cassava planting has been mechanized. Farmers use specialized cassava planters that can simultaneously create furrows, place cuttings, cover them with soil, and press the ridges, all in a single pass. Such machines can plant 1 to 2 hectares per day, significantly reducing labor and saving time. After planting, a light watering may be needed if the soil is dry. Within 7 to 10 days, the cuttings will take root and sprout, beginning their gradual transformation into full-grown plants. An interesting fact is that the long, pointed lobes of cassava leaves are sometimes mistaken for cannabis, a surprisingly common misconception in both rural and urban areas. With proper cultivation techniques, cassava plants can reach a height of 1.5 to 3 meters, with vigorous root development that leads to high yields at the end of the 8 to 10-month growing cycle. This marks the foundation for a bountiful harvest, completing a journey that began with humble stem cuttings. At large-scale cassava farms, modern machinery is brought in to streamline operations. On wide, flat fields lined with neatly arranged rows of cassava, specialized harvesters move steadily along the beds. At the front, rotating blades swiftly clear the mature stalks. Immediately behind, a set of digging blades sinks into the soil, gently lifting the entire root system and pulling out clusters of cassava tubers. As the machine completes a row, the cassava plants vanish, leaving behind loosened soil and exposed roots near the surface. Workers then step in to collect any remaining tubers by hand and place them into large baskets or sacks positioned along the rows. Once full, the sacks are hoisted onto waiting trucks at the edge of the field. The entire process is smooth and efficient. Each pass of the harvester can save hours of manual labor, dramatically increasing harvesting productivity, especially during peak seasons. In smaller farms or areas with sloped terrain, hard soil, or irregular planting patterns, cassava is still harvested by hand. Though more labor-intensive, this traditional method can still be highly effective when done correctly. In loose, well-aerated soil, farmers can uproot entire cassava plants by hand without the need for hoes or crowbars. They then use specialized knives to separate the root clusters from the stems and gather them into baskets or sacks. It's a physically demanding task that requires strength, patience, and technique, especially under scorching sun or in hardened soil. In some regions, farmers first cut the stalks, then use a digging tool to lever the root base out of the ground. Once lifted, the roots are shaken clean, separated from the cluster, and placed into containers for transport. And when the trucks are finally filled to the brim, they roll away from the fields, marking the end of a fruitful harvest season and the beginning of a new journey, as these soil-covered cassava roots are transformed into pure white starch, ready to serve the food and industrial sectors. As soon as the trucks arrive at the factory, the cassava roots are unloaded at the receiving area and temporarily stored in a holding yard. Depending on the scale and capacity of the facility, the plant can handle up to several thousand tons of fresh cassava per day. At this stage, a preliminary inspection is carried out to remove damaged, rotten, or heavily contaminated roots before entering the processing line. At this stage, the raw cassava roots are divided into two main processing streams, depending on their intended end use. One portion goes through the dry processing route, where the cassava is thinly sliced, typically to a thickness of 3 to 5 millimeters, to facilitate faster and more uniform drying. It is widely used in the animal feed industry due to its high energy value and also serves as a key input for fermentation-based industries, such as the production of bioethanol, vinegar, organic acids, and various other bio-based products. The other portion is directed toward further processing into refined cassava starch. From the storage yard, an automated conveyor system continuously feeds the selected roots into the cleaning section, marking the beginning of a fully enclosed and high-capacity processing line. From the receiving conveyor, the cassava is transferred into a continuous washing system, typically a horizontal drum washer. This machine operates by rotating while internal spiral paddles and high-pressure water jets work together to remove all soil, sand, mud, and the thin outer skin from the surface of the roots. As the drum spins, the cassava roots tumble against the rough inner surface and against each other, causing dirt and skin to peel off naturally without the use of chemicals. In industrial processing, cassava roots are not completely peeled as they are in traditional methods. Instead, they are thoroughly washed and mechanically cleaned to remove dirt and the outer skin, allowing for maximum starch retention. As a result, a certain amount of cyanogenic compounds, primarily linamarin, may still remain in the roots, especially in bitter cassava varieties. And to eliminate this natural toxin, we must now take a closer look at the critical processing steps that follow. After washing, the cassava is passed through a manual inspection stage. Here, workers remove any damaged, bruised, or diseased roots that machinery might not detect accurately. The selected cassava is then either cut into smaller pieces or left whole, depending on the requirements of the next step, grinding. At this stage, the cassava is fed into either a roller crusher or a high-speed blade grinder, where it is crushed into a pulp. This mixture consists of starch dissolved in liquid and fiber that has not yet been separated. This is a crucial step that breaks down the cellular structure of the roots, allowing for the maximum release of starch from the raw material. The pulp mixture after grinding, consisting of starch dissolved in water and undetached cassava fiber, is transferred to a centrifugal or vibrating screening system, depending on the technology used by the factory. In a centrifugal sieve, the mixture is pumped into a high-speed rotating drum covered with a fine mesh screen. The centrifugal force pushes the mixture outward toward the screen, allowing the fine starch and liquid to pass through the mesh, while cassava fibers and larger impurities are retained and discharged separately. The separated fiber doesn't go to waste. It's collected and used as rough animal feed, as it still contains a small amount of starch and beneficial fiber, making it a nutritious meal for our cows. Do you agree with these, Moo? The next step is dewatering. Various methods are used depending on the scale and level of automation of the factory. At medium and small-scale facilities, a filter press is commonly used. In this system, starch slurry is compressed under high pressure between thick filter plates, effectively removing most of the water from the mixture. The result is a semi-dry starch cake with a moisture content of around 40 to 45%, which is soft, white, and moldable. This semi-finished material is essential for the subsequent drying process. Although the filter press operates in cycles, it is easy to maintain, simple to operate, and well-suited for medium-capacity production lines. In large-scale industrial factories, where high output, continuous operation, and full automation are required, the dewatering process is typically upgraded to a rotary vacuum filter. This equipment uses a rotating drum combined with vacuum suction to continuously extract water from the starch slurry. As the drum rotates through the starch tank, a thin layer of starch adheres to its surface and is gradually dried by suction through a filter cloth. This is also a critical stage for removing most of the natural toxins found in cassava roots. After grinding, cyanogenic compounds are released and dissolve into the water. Through continuous steps of fiber separation, filtration, and dewatering, the majority of hydrogen cyanide is carried away with the liquid waste, significantly reducing the toxin content before the drying phase begins. During the dewatering process, a large volume of wastewater is generated from stages such as root washing, grinding, sedimentation, and filtration. This wastewater contains residual starch, organic matter, and suspended solids, which, if not properly treated, can cause serious pollution to surrounding water sources. To manage this, factories typically implement multi-stage wastewater treatment systems, including primary sedimentation, flow equalization, biological treatment, and final disinfection. Some modern facilities also incorporate biodigesters, which recover biogas from sludge, reducing emissions while generating renewable energy to power the production line. This is a key factor enabling the cassava starch industry to grow sustainably and in an environmentally friendly manner. Meanwhile, the semi-dry starch is fed into a flash dryer, where high-speed hot air rapidly evaporates the remaining moisture in just a few seconds. The heat source for this drying system typically comes from biomass burners, coal, firewood, or gas, combined with automatic temperature control systems to ensure energy efficiency and consistent product quality. The result is a fine, white cassava starch powder with a standard moisture content of less than 13%. After drying, the starch exits the flash dryer at a high temperature and must be cooled immediately to preserve its quality. A forced air cooling system is used, blowing controlled streams of cool, filtered air through the starch as it moves along the conveyor. Once cooled, the starch passes through a sieving system, typically a high-frequency vibrating screen or a roller-type disintegrator. These machines are designed to gently but thoroughly break down any remaining agglomerates formed during drying. This step ensures the starch has a fine, uniform texture, removes any oversized granules or residual impurities, and prepares it for precise and consistent packaging. Once the starch meets quality standards, it is transferred to an automatic packaging system. Depending on demand, the product is packed in 25 kilograms or 50 kilograms bags, or in jumbo bags weighing up to 1 ton, suitable for both consumer markets and industrial processing. From humble, soil-covered roots to a refined, pure white powder, through human hands and modern technology, a remarkable journey unfolds, producing starch that nourishes people, powers industries, and connects the world. Rice is a staple food worldwide, and in the US, it comes in several varieties, primarily long grain, medium grain, and short grain. Long grain rice, like the popular jasmine and basmati, is slender and stays fluffy when cooked. Medium and short grain varieties are plumper and stickier, making them ideal for dishes like sushi or risotto. The appearance of rice varies depending on the variety, but in general, it is found in shades of white, brown, or even black and red, depending on whether it is processed or left whole grain. Rice plants thrive in warm, humid climates and require plenty of water. Unlike crops that can withstand dry spells, rice needs constant moisture, which is why it is often grown in flooded fields called paddies. The best growing conditions include temperatures between 70 to 100 degrees Fahrenheit and well-drained, loamy soil with a pH between 5.5 and 7.5. These conditions help ensure the plants develop properly, allowing them to produce healthy grains. In the US, rice is mainly cultivated in Arkansas, California, Louisiana, Mississippi, Missouri, and Texas. Gone are the days when farmers had to cut rice by hand with sickles and spend days processing it manually. Rice harvesting in the U.S. has evolved into a highly mechanized and efficient process, primarily using combine harvesters, large and powerful machines that can complete in minutes what previously took farmers days to accomplish. These machines not only cut the rice, but also thresh, separate, and clean the grains in a single operation, making them indispensable in modern rice farming. The introduction of combine harvesters has dramatically transformed rice production, increasing efficiency, reducing reliance on manual labor, and ensuring that rice can be harvested quickly before adverse weather conditions impact the yield. A combine harvester is a sophisticated piece of machinery with multiple essential components, each serving a specific purpose to ensure a seamless harvesting process. At the front of the machine is the header, a critical attachment responsible for cutting the rice stalks and feeding them into the harvester. As the stalks are drawn in, they enter the threshing drum, which plays a key role in separating the grains from the stalks and husks. This stage is crucial, as it allows the grains to be detached efficiently without damaging them, ensuring the maximum yield from each field. Once the grains have been separated, they pass through sieves and a cleaning system, where any remaining debris, broken husks, or unwanted materials are filtered out, leaving behind clean, high-quality rice. This meticulous process ensures that only the best grains proceed to the next stage. The harvested rice is then stored in a grain tank, which temporarily holds the rice before it is unloaded into waiting trailers or trucks. This unloading system allows for a continuous harvesting flow, ensuring that fields can be cleared efficiently and promptly transported to processing facilities. One of the most significant advantages of using combine harvesters is their ability to increase harvesting efficiency by up to 50 times compared to traditional manual methods. This dramatic improvement not only saves farmers time, but also reduces labor costs and minimizes grain loss. With rice being such a vital staple food, the ability to harvest quickly and efficiently ensures that more rice reaches processing plants, meeting the demands of both domestic and international markets. The integration of industrial machinery into rice farming has revolutionized the industry, making large-scale production feasible while maintaining high standards of quality. In addition to efficiency, modern combine harvesters incorporate advanced technologies that optimize yield while minimizing environmental impact. Many of these machines are now equipped with GPS tracking systems, which enable farmers to precisely map their fields and follow optimized harvesting patterns. This precision reduces waste, prevents over-harvesting in certain areas, and maximizes the use of available land. Furthermore, many combine harvesters feature adjustable cutting heights and grain loss sensors, ensuring that every stalk of rice is harvested effectively while reducing unnecessary waste. Beyond their immediate harvesting capabilities, combine harvesters also contribute to sustainability in agriculture. By streamlining operations and reducing the need for extensive manual labor, these machines allow for more controlled water and soil management, ensuring that rice paddies remain fertile for future planting seasons. With innovations such as automated moisture detection systems, farmers can make informed decisions on the best times to harvest, preventing spoilage and maximizing the longevity of their crops. The adoption of such cutting-edge technology continues to push the boundaries of agricultural efficiency, positioning U.S. rice farming as a model of innovation and sustainability. In an era where global food demand is increasing, the ability to produce rice efficiently while conserving resources is more critical than ever. Farmers who incorporate these advanced techniques not only improve their own profitability, but also contribute to a stable and sustainable global food supply. Once rice is harvested, it doesn't go straight to store shelves. Instead, it undergoes several processing steps in factories to make it safe and appealing for consumers. The first step in processing is cleaning and drying. Freshly harvested rice contains moisture and impurities like dirt, stones, and husks. Large industrial dryers reduce moisture levels to prevent spoilage. The drying process is crucial because improperly dried rice can develop mold or spoil before it reaches consumers. After drying, the next step is hulling, where the outer husk is removed, leaving behind brown rice. For those who prefer white rice, the process continues with milling, where the bran layer is polished off, revealing the soft, white grains underneath. This process is done carefully to ensure that the grains remain intact and maintain their quality. However, milling reduces the nutritional content of the rice, which is why some manufacturers enrich white rice with vitamins and minerals before packaging. The next crucial step is sorting and grading, where high-tech machines use lasers and sensors to remove broken or discolored grains, ensuring uniformity. This step ensures that only high-quality rice makes it to consumers. Finally, the rice is packaged and stored in temperature-controlled warehouses before being distributed to markets. Some rice is processed further into rice flour, rice bran oil, or instant rice products to meet the diverse needs of consumers. Factory processing ensures consistency, food safety, and efficiency in the supply chain. With rigorous quality control measures in place, American rice producers can guarantee that their products meet both domestic and international food safety standards. This level of precision ensures that the rice sold in stores remains fresh, nutritious, and free of contaminants. Before farmers can even think about harvesting, they must first prepare the land and plant rice correctly. Rice farming begins long before the first green shoots appear in the fields. The first step is soil preparation, where farmers plow and level the fields to create a smooth surface for planting. Water management is crucial, so they set up irrigation and drainage systems in advance to maintain proper moisture levels. Farmers employ two primary planting methods: dry seeding and water seeding. In dry seeding, seeds are planted in dry soil and later flooded with water. This method allows for better weed control and makes the rice more resistant to lodging, falling over due to wind or rain. In water seeding, pre-germinated seeds are directly sown into flooded fields, a method that helps suppress weeds naturally but requires precise water level management. Once planted, rice fields require careful maintenance. Fertilization and pest control play a significant role in ensuring a healthy crop. Farmers use a combination of organic and synthetic fertilizers to provide essential nutrients. They also employ integrated pest management techniques to keep harmful insects, weeds, and diseases at bay without excessive chemical use. Throughout the growing season, water management is carefully controlled to maximize yield while minimizing environmental impact. With the right preparation, rice plants grow strong and healthy, leading to a bountiful harvest when the time comes. The use of modern agricultural techniques has allowed American farmers to optimize rice production while maintaining environmental sustainability, ensuring that the U.S. remains a competitive player in the global rice market. Harvesting 9.97 million tons of rice in the U.S. is no small feat, and it requires a combination of advanced technology, skilled farmers, and efficient processing systems. Peas are one of the standout crops in American agriculture, playing a crucial role in providing fresh, frozen, or canned peas for the food industry. They're commonly grown in states like Washington, Wisconsin, Oregon, and Minnesota, where the cool climate and well-drained soil create the perfect conditions for their growth. Not only are peas a staple crop in the US, but they also thrive globally, especially in Europe, where they hold a prominent place in agriculture and cuisine. Farmers worldwide have mastered the art of growing peas, combining traditional farming techniques with modern technologies to achieve high-quality yields that meet global demand. Every story about green peas begins in the fields. In early spring, when soil temperatures reach around 40–45 degrees and the threat of frost has passed, farmers get to work planting peas. The first step is soil preparation. Advanced machinery like disc harrows and rotary tillers are used to loosen the soil, improve aeration, and remove weeds. This creates the perfect environment for pea seeds to germinate and grow. Next, farmers apply organic or mineral fertilizers evenly across the fields using spreaders, ensuring the soil is nutrient-rich to support healthy crop growth. Once the soil is ready, the next step is planting. Pea seeds are often treated with nitrogen-fixing inoculants before sowing to enhance their natural nitrogen-fixing ability and protect them from soil-borne diseases. Using modern seed drills, farmers carefully place the seeds at a depth of 1 to 2 inches below the surface, spaced 1 to 2 inches apart in rows that are 18 to 24 inches apart. Thanks to advanced technology, the planting process is not only quick and efficient, but also highly precise. With these tools, farmers can plant dozens of acres in just one day, setting the stage for a bountiful pea harvest. Once the pea seeds sprout, American farmers use automated irrigation systems to deliver consistent water supply, ensuring the ideal moisture levels for the plants to thrive. Fertilizers are applied periodically using modern spreaders, allowing the plants to absorb nutrients effectively without waste. On vast fields of green peas, sophisticated sprayers glide smoothly between rows, coating the leaves with a fine mist of protective solutions to safeguard against pests and diseases. Thanks to the integration of modern technology, caring for peas is efficient and ensures the plants grow strong and produce optimal yields. Green peas grown in the US are typically ready for harvest about 50 to 70 days after planting. The ideal time to harvest is when the pods have reached full size, are plump, and yet remain tender. Across the vast temperate fields of America, pea harvesting has evolved far beyond manual labor, thanks to advanced machinery. Two primary types of harvesters are commonly used: conventional pod harvesters and integrated seed harvesters. First, we come to the whole pea harvester. Conventional pod harvesters are basic machines designed to collect entire pods from the plants. As they operate, a front-mounted reel system gently guides the pea plants into the machine. Flexible stripping fingers or rotating brushes detach the pods from the vines without damaging them. The collected pods are then transported via conveyor belts to large storage bins at the rear of the machine. Meanwhile, the plant stems and leaves are left behind in the fields to decompose naturally, acting as a green manure that enriches the soil. This approach not only saves the farmers from post-harvest cleanup, but also enhances soil fertility for future crops. These machines are particularly popular on large farms due to their lower cost and quick harvesting efficiency. However, since the pods remain intact, additional processing is required at the factory to shell the peas. Next, we will learn about the harvesting process, where the shell has been separated from the seed. On large-scale farms, or in regions specializing in frozen pea production, integrated seed harvesters are the ideal choice. These machines not only harvest the pods, but also separate the peas from their shells right in the field, streamlining the process and saving valuable time in post-harvest handling. These harvesters operate much like conventional ones, with a front reel system that gathers the pea plants. However, instead of keeping the pods intact, these machines are equipped with an internal shelling chamber. The pods are fed into the chamber, where high-speed rotating drums gently strip the peas from their shells. The empty shells are then crushed and returned to the field through a rear discharge system. The fresh, tender peas are transported via conveyor belts to large storage bins at the back of the harvester. This system ensures that the peas remain intact and maintain the highest quality standards. Picture an early morning on a sprawling pea field where massive harvesters line up in formation, slowly moving through rows of lush green pea plants. The hum of engines blends with the rustling breeze, and the faint, fresh aroma of peas fills the air, creating a harmonious and vibrant scene of agricultural labor. These modern, integrated harvesters not only help farmers complete their work faster, but also ensure uniform quality for every pea harvested. Once collected, the fresh peas are promptly loaded into large storage bins and transported to processing facilities. Harvesting peas isn't just an agricultural task, it's a seamless blend of human effort and cutting-edge technology. From basic pod harvesters to advanced integrated machines, each tool brings unique value to meet the diverse needs of the agricultural industry. With every tender, green pea we enjoy, we can taste the dedication of farmers, the advancements of technology, and the love for these bountiful fields. It's this perfect harmony that makes peas a wonderful gift, crafted together by nature and humanity. In addition to machine harvesting, some green peas are harvested by hand. Farmers walk slowly between rows of pea plants, carefully lifting each leafy branch to find plump, ready-to-pick pods. With precision and care, they gently pluck the pods from their stems, preserving their freshness while leaving the lush greenery intact for future harvests. Once harvested, the peas are swiftly transported to the factory to begin processing. Upon arrival, workers wash their hands and don protective gear to ensure food safety and hygiene. The pods are then trimmed, with any substandard ones removed in preparation for cleaning. Next, the peas are fed into an automated washing system where all soil and impurities are thoroughly removed. Finally, the peas are carefully packaged using advanced assembly lines, ensuring they are ready for storage and distribution. Next, we come to the process of processing frozen green beans. When the peas arrive at the factory, they are unloaded into large intake hoppers. The shelled peas are then transported via conveyor belts through a screening system to remove impurities such as soil, stones, and leftover stems or leaves. Next, advanced optical sorting machines inspect each pea for size, color, and quality. Only the plumpest, brightest green peas make the cut, while those that don't meet the standards are discarded. After sorting, the peas move to the washing area. Large water tanks and high-pressure sprayers combined with air bubbles ensure that every pea is thoroughly cleaned, removing dirt and bacteria. Some factories use chilled water during this step to maintain the pea's freshness before proceeding to the next stage. Blanching is a critical step in preserving the vibrant green color and natural sweetness of peas. The peas are submerged in hot water at temperatures between 185 degrees and 203 degrees Fahrenheit for a few minutes. This process kills bacteria and halts enzyme activity that could cause spoilage. Immediately after blanching, the peas are rapidly cooled in an ice water bath to lock in their crisp texture and freshness. The selected peas are subjected to quick freezing at -40 degrees. This flash freezing process ensures that each pea is individually frozen, preserving its freshness, color, and nutritional value. It also allows the peas to maintain their quality over extended periods of storage. After freezing, the peas move to the packaging area. There are workers standing here to remove substandard seeds. Automated packing machines accurately weigh and portion the peas into bags, which are then vacuum sealed or filled with preservation gases to extend shelf life. In addition, frozen green beans are also packed into cans using modern production lines.